Okay, so from our last discussion, we ended up somewhere around here. So we're analyzing a pretty simple circuit, just a inductor and a resistor in series. When we switch a signal here, so if we have a switch here and we're switching it at a certain frequency, the output is the current through here times the resistance, and the current is just the current through the inductor. Because we're switching it, it's ramping up and then it's ramping down. And the next step is adding a capacitor on this node right here. And what happens is the ripple gets smoothened out or gets squished in. It gets smaller. The black line is before we add the capacitor, and the blue line is the voltage after we add the capacitor. Meaning that some of this ripple current is being absorbed into the capacitor. Because the average stays the same, but the ripple is smaller. So the capacitor is absorbing the ripple current. We can use this formula here for the capacitor, where the voltage on the capacitor is 1 over the capacitance times the integral of the current. Or we're summing up a bunch of currents with every piece of time, and we're adding that together, and that's how we get our voltage. So a capacitor is like a bank of water, and every second we add a little bit of water, then that's going to be able to tell us where the water level is. So if the water level is the potential, and a little bit of water is the current, if we measure the time and the flow of current, we'll be able to get how much voltage is on there, and it's proportional to 1 over. Let me just make a distinction here. This is just the voltage graph to show you what's happening. This is the current graph. So it's absorbing the excess currents here. So if the average is the same, then the only areas we're looking for are the area under the graph is here and here. And we can take a look at one of them. So to find the area here, it turns out this is actually the period divided by 2. Turns out this height is delta divided by 2. And then the area for a triangle is the base times the height divided by 2. So this is our area now for the excess current that the capacitor is absorbing. We can substitute that in here, so we get that VC is equal to 1 over C 1/2 times T 1/2 times delta IL 1/2. Let's simplify this, so 1 over C 1 over 8 T times IL. We can substitute this guy for either the IL on or the IL off from before. We can do it on the off period. So if you recall, okay, let's make this substitution, and we're left with 1 over C 1 over 8 times T times VO 1 minus DT. Okay. And we need to rewrite this as the delta VC, because we'll replace it with the area and not the integral. Now let's divide that both sides by VO. So this will cancel. And if you recall, delta VC over VO is just the ripple ratio. So what we're left with here is T squared 1 minus D 8CL. I think I've simplified it correctly. And this is just our ratio. We can write that as percentage ripple, and solve for C. So now we get t squared 1 minus d 8L p percentage ripple. And now we can size our capacitance to fit the desired voltage ripple. So if we want a ripple of a couple of percent here, let's say our output voltage is 5, and we want it to ripple between 5.1 and 4.0 or 4.99. Calculate the percentage. So let's say that's 5% for the sake of argument. So replace this one by 0.05. Because this, you can rewrite this as t squared over 1 over the frequency, switching frequency squared, if that's easier for you. So if you've been given the switching frequency, you can rewrite this as C equals 1 minus d squared 8L percentage ripple. I like to just put parentheses around this to let everyone know that it's our desired percentage ripple. And here we go. This is how you size the capacitor for the buck converter. I hope this helps. I hope I was clear. I'm not the best professor, but maybe this helps. I'll put this document out on my Patreon in case you want to look over it.